Okay. Good afternoon. In fact, we will have around 20 to 30 minutes lecture. We will then all our lectures will be finished, and then we have around 20 to 30 minutes for question and answer before our in-class test too. Okay. Recently, I think before next weekend, I will try to return all your assignments and in-class tests, the assessment back to you. Okay. And also, we will have a revision as scheduled. So, because it's a take-home examination, it's challenging for me to prepare for the examination questions. Okay, please try to understand. Maybe for our revision, so I will not let you know too many details of our questions. Okay. Firstly, let's start our lecture. So, in fact, we have introduced for our vapor compression refrigeration system, we have several main components, including evaporator, condenser, throttling valve, and compressor. And for the four main components, so we have the evaporator, and condenser. So they are heat exchangers. Okay? They are heat exchangers. Okay, they are heat exchangers. So we need to understand for heat exchangers, so there are two working fluids exchange heat. Okay, so we apply the first law for open system. Okay, we can apply the first law equation, energy equation, for the heat exchangers. And also, in fact, for our multi-stage for the flash chamber is also we can consider is mixing. So for flash chamber, we can also consider like a heat exchanger. Okay, and for the compressor, in fact, we have introduced there are four main types of compressors. So we have a reciprocating compressor, screw compressor, and centrifugal compressor. And previously, we mainly introduced reciprocating compressor. So for reciprocating compressor, even through our tutorials, we know that in fact we have to be careful if it's the numbers of the cylinders and it's single acting or double acting, etc. For the reciprocating compressor, we understand that so it's per cycle. So there are 4 strokes, including delivery, induction, compression, delivery, and expansion. So that's called one revolution or one cycle. Okay, one cycle. And the working principle is different for reciprocating compressor. Is based on to reducing the volume. Okay, reducing the volume. So therefore, so for a closed system, if we're reducing the volume, then we can increase the pressure. And then the other type is a centrifugal compressor. So for centrifugal compressor, we know it's the transfer, energy transfer from the angular momentum, okay, to the temperature, to the pressure rise. And usually, it's a centrifugal compressor suitable for large volume flow rates. Usually, the larger the plant, the more likely it is that a centrifugal machine will be. Okay, usually centrifugal compressors are suitable for large volume flow rates and for large cooling capacity. And let's have a look at the centrifugal compressor. In fact, it's the same, the centrifugal pump, centrifugal fan. So for our pumps, even for the pumps and fans in our daily life, they are also using they called centrifugal pumps and fans with a similar working principle. Okay, for the centrifugal compressors, so we can see it's much faster. Okay, so that's the reason why it's suitable for large volume flow rates. So this is a large volume flow rate of refrigerants. So we can say its rotating speed is much larger. Okay, so we remember for reciprocating it's only several hundreds, okay, per minute. So there is our compressors can complete hundreds of cycles. And so for the rotating speed, it's much larger. So therefore, it's suitable for large volume flow rates. And also for the isentropic efficiency, we can see this is the compressor efficiency. So it's 70 to 85%. And usually for larger larger capacity centrifugal compressor or chiller, so the compressor, the isentropic efficiency will be higher. So how to control the flow rates? You think so? How to control the volume flow rates? In fact, based on there are main two types: variable speed or the variable speed control or inlet guide wand control to control the volume flow rates. So so for that part, for building services discipline, in fact, we will learn it via air conditioning, ventilation, heating, ventilation, air conditioning subject. So now let's look at the working principle of. So before we have any questions related to centrifugal compressor, I think it's important for us to understand the working principle of a compressor, the centrifugal compressor. So in fact, for centrifugal compressor, we can see here the pictures shows the two simplified sections through the main components of a centrifugal machine. Okay, the main component including the impeller. Okay, the impeller here. So this is impeller here. The impeller is rotated at high speed inside a casing. Okay, this is a casing. This is a casing. Okay, this is a casing. Typical speeds. Okay, it runs from 3,000 to over 20,000 revolutions per minute. And the vapor enters. So we can see, in fact, it's special because when we look at even for the pump, we know the inlet, okay, is into the eye. Okay, no, not like this. Okay. This is the eye. Okay, this is the eye. Okay, so this is the eye of the impeller, the eye. Okay, and the vapor enters the eye of the impeller in an axial direction. The flow is then turned through. We can see changing direction through 90 degrees Celsius as the vapor passes through curved passages. Okay, the curved passages. I think from here it's leaving like it's leaving. Okay, the direction. Okay, so the direction. So the direction, the leaving direction in the passage. and the vapor flows outward, and the flow is then turned through, so coming, then changing, turned through 90 degrees as the vapor flows outward, its pressure increases due to the centrifugal effects. And it leaves the impeller tip at an increased pressure and a very high speed. From the impeller, it is discharged to diffuser passages where the velocity is induced, resulting in a further increase in pressure before it enters the discharge pump. So we understand. So the flow enters. Is the eye of the impeller. Then it turns through 90 degrees, and then due to the centrifugal effects, so it leaves the impeller. Impeller tip at an increased pressure and very high speed, and then when it starts discharge to diffuser passages, then the velocity is reduced, which will result in a further increase of the pressure before it enters the discharge pipe. So this is the working principle of the centrifugal compressor. So for the centrifugal compressor, besides we can use the conventional one formula at any time. If we know this is the discharge and inlet, this is entering flow enthalpy, and this is delivered vapor. Delivered pressurized vapor is specific enthalpy. Whenever we know the enthalpy, we can use the enthalpy difference to calculate so the work input by the centrifugal compressor. But however, for the centrifugal compressor, we can also calculate based on its impeller tip velocity, because we understand that this is the impeller. This is the impeller. This is impeller tip. So we know the flow will leave. Will leave. The useful one is leaving. So at the impeller tip. We know for the tip it has for the tip itself, impeller tip itself, it has a speed, and also for the vapor, the pressure will be increased. And the velocity will be increased, and it will leave in the passage, leave the impeller tip with the actual direction of flow. However, the tangential, the component of flow velocity, is valuable. For the compression. And now let's have a look how to calculate. So how much power is for the power calculation is the power of the impeller tip, the worked by the impeller tip on the vapor. So as we know, in fact, for the calculation power, it times the force. So if there is any force, so in the direction of the force, we have a velocity. Okay, is distance moved in the direction of the force. So per second. Then in the calculation, we can calculate power. Okay, we can calculate power. Then we are thinking about what's the force. The impeller tip, the force of the impeller pressed on the vapor. So then you push the vapor. Okay, you speed up the vapor. And then we found, in fact, we are using, this is the mass flow rate of the vapor. This is the tangential component of the vapor velocity. Then we know it's like force times the distance over time. So it's also same to the to the momentum. Okay, then in fact for the force, in fact we can be calculated the force on the vapor is the mass flow rate of the vapor times is a tangential component of the vapor, because this one is affected by the tip, by the impeller. Then this is the force, and in the force of the then in the force of the tangential momentum, then we times the impeller tip velocity. Okay, that is the distance per second. So that means because it's the impeller tip on the power of the impeller tip on the vapor, this is the effective force times the movement distance over per second of the impeller tip. So is the impeller tip velocity. So therefore, for the centrifugal compressor, we can also use this equation to calculate the power conducted, the power input by the compressor. Okay, of the compressor. So then we understand that mass is mass flow rate of the vapor, and this velocity is the tangential component. Is the tangential component of the flow. Okay, it is used to calculate the force on the vapor. And then this is the impeller tip velocity. This is impeller tip velocity. Okay, is here. Okay, is here. So this is used to calculate the distance per second. And then you are curious about these two velocities, why they are not the same. Because this is the impeller tip velocity, it shall be equal. Okay, ideally it shall be equal to the tangential component of the flow velocity. So ideally, so these two velocities shall be same. Okay, so ideally, these two velocity shall be same. Okay, shall be same, because so for the impeller tip velocity shall be same to the tangential component of the vapor velocity, leaving the near the impeller tip. Okay, because as we learned, so the delivered vapor will leaving the impeller tip, okay, into the passage. So therefore, however, actually the tangential component of flow velocity will be smaller than the tip velocity. Okay, it is smaller. Okay, it is smaller. However, ideally it shall be same. However, in actual, so this velocity, the tangential component of the vapor velocity is smaller than the impeller tip velocity. So therefore, we are using a slip factor to describe, to measure, so the effective. So it's called a slip factor. It's defined by the ratio of the tangential component of the vapor velocity over the impeller tip velocity. So then we know for the impeller tip velocity, we recall what we have learned. So for mathematics, then we know the calculation becomes. So this is the tangential component of the vapor velocity, the impeller tip velocity will be equal to the, so we can see the equation, D is the diameter of the impeller of the compressor, and then times the, so that's for 1 per revolution. This is the distance, okay, the moving distance. Or per cycle or per revolutions. So this is the let me see, okay. And so this is, in fact, this value is the distance of the impeller tip moved. Also, it's the same to the parameter of the how to say, the cycle. So it's equal to the geometry parameter. Okay. Then if v times per second, n times the n is the speed in revolution per second. So then we can calculate if we know the geometry design of the compressor and also the compressor speed. So then we can calculate. Then we can calculate the. Then we can calculate the impeller tip speed. So therefore, we can see we can replace the equation by using only we know the vapor tangential component of the vapor velocity. Okay, is the mass flow rate times the slip factor times the square of tangential component of the vapor velocity. Okay, if they are same, okay, we can get the relationship. Okay, between the enthalpy difference and also the tangential component of the vapor. So later you will know through tutorial we will understand why we have this one. That's because later we know sometimes one stage is not enough. We shall choose several stages to avoid too high vapor tangential component of the vapor velocity. Okay, we will further explain and learn through our tutorials. So then we have one example. Let us to compare. So the effect of part load operation on evaporator temperature. So with for different centrifugal compressor or reciprocating compressor, then we need to understand that. So like if a centrifugal machine, there is little change at part load in evaporator temperature over a wide range capacity. However, with the reciprocating machine, the capacity is reduced by increasing the pressure ratios, so which decreases the volumetric efficiency. So for such, I will leave it to you. You know how to analyze analyze the problems by using our what we have learned. And also, there's examples we can see. Let me see. Okay. We have an example in our teaching note. So regarding compressor, okay. So for our refrigerant refrigeration plant. So for this refrigeration plant, so with the centrifugal compressor, and they in fact, is we know the isentropic efficiency and the pressure ratio and the speed. Then we ask to calculate the COP and the mass flow rate and the volume flow rate of refrigerants. So I think maybe we leave. You can read the solutions first from our teaching note. I think we will leave them to our tutorials because I think more of you maybe expect me have question and answer session. Okay, so example number 4, we will leave it to tutorial session. And however, so for compressor, as we learned, in fact, for compressor, sometimes if there is a high pressure ratio, we need multi-stage compression. Okay, look at here. So one stage, I think. No tip for in-class test 2. Okay, you have to understand because it's an open book. It's difficult. Okay, and so later maybe I let you know. So the questions. So the details of our in-class test 2, but no tips. And for stage compression, can achieve higher compression ratios and compressed gas can be cooled between stages of intercooler or 1, 2 or more stage compressor. In fact, okay, I let you know. So there is one question. So for in-class test 2, okay, regarding. Okay, a last question of our in-class test 2 regarding multi-stage compression. So also you know we have an intercooler. Okay, I also ask you to calculate the heat transfer of intercooler. Okay, intercooler. So there's a last question for in-class test 2 is regarding this question with the multi-stage the compressors connected directly in series. Okay, so we can see if in series we have this is the I. Okay, this is discharge. Okay, we can see this is discharge. This also discharge. Oh, there's even this one. I think this one is discharge. Okay, I think this 3 stage. I think 2 stage. Oh, I see. This is 2 stage. This is 2 stage. So the discharge. I think here is intercooler. Okay, intercooler. Okay, as I just have mentioned, for in-class test 2, the last question is regarding such a question. So 2 stage compression. So the in series, but with the intercooler. Okay, so it's like this. So with the main-stage compression with the intercooler. So you know for intercooler it's a heat exchanger. It's a heat exchanger. Okay, you need to know how to calculate the heat transfer of the intercooler. Okay, is our heat exchanger. So the high ratios of compressor ratio occur in refrigeration cycle when the evaporating temperature is much lower than the condensing temperature. Compressing the gas in 2 or more stages can improve volumetric efficiency and reduce the power requirements. The use of intercooler between stages will lower the gas discharge temperature and also improve performance. So ideally, the intercooler will bring the temperature of the gas leaving the intercooler down to the ambient air. So when the pressure, so we have the pressure, I think we have the pressure 1, 2 and 3 same, okay? 2 and 3 same. Okay, so this is this is 3. So when the pressure 2 is okay with the same compression ratio, okay, of each stage, then with the minimized work. This we have examined, I think, during our in-class test 1. However, we have to understand we have intercooler to cool down. Usually, so it's compressed, then deliver temperature very high, then we cool it down back to the ambient temperature again. Okay, so this similar question will be examined in our in-class test 2. Okay, now I think I will stop recording. We have around 20 minutes, so for you to see for question and answer, then and also you prepare for the in-class test. So for me, I wish you could submit, okay, on time for fairness. If you cannot, you fail to submit, you can send by email to me immediately, but you need to provide me your excuse. Okay, thank you.